So it is my great pleasure to introduce to you Professor Adam Bobrowski from Technical University of Lublin. He holds master and PhD degrees from University Maja Skłodowska. And then he moved for 5 years to Texas, to Rice University and Houston University, and of course still has contacts and visits Texas quite often. He's a specialist in functional analysis and stochastic processes, and sort of to join these two domains by his specialty, which are semi-groups of operators. And besides theoretical mathematics, theoretical constructions, he uses these tools in various applications in biology. Roughly speaking, 3 themes in biology. One is the gene expression and regulation, path signaling in living cells, but also in the population genetics, and recently in agrophysics. Especially, he's a master of boundary conditions, of interesting boundary conditions. In 2020, he got the Hugo Steinhaus Prize given by Polish Mathematical Society. I would like just to add, then he's very prolific book writer. Six books, yes, or 7, no, even 7 books. I think he has written 7 books, either by himself or with co-authors. Adam, the Zoom is yours.
Well, thank you very much for this very nice introduction. Just a short question. Can you hear me well?
Yes, very well.
Okay, so also a very small correction. My PhD was from Institute of Mathematics of the Polish Academy of Sciences.
I'm sorry for that, or maybe there is some wrong information somewhere in the internet.
No, not a problem.
Sorry for that.
No, not a problem at all. First of all, I would like to apologize for not being there in person. Just my health condition didn't allow me to come. It would be very nice to be there with you. Coming back to Jacek's introduction, in today's talk, there will be no biology at all, except maybe for the notion of semi-permeable membrane. And as Jacek has mentioned, I am very fond of boundary conditions, so boundary conditions will play a significant role in this talk. What I'm going to speak about is Skew Brownian motion, and this is an object which was studied already in 1970s of the previous century, but recently I came across this object in 2 surprising ways, and this is precisely the subject of my talk. So the outline is quite simple. I will give you basics of Brownian motion and its variants on the half axis, and this will lead us directly to modeling semi-permeable and permeable membranes. Then these membranes will lead us to Skew Brownian motion, which will be defined somewhere in the middle of the talk. And finally, I will give you another view of a Skew Brownian motion from the perspective of a kinetic model, which I have studied recently. Jacek has mentioned that I am interested in biology, but this kinetic model comes directly from physics. And I will speak about it a little bit more later. Okay, so since this is a talk mostly for young people, I will start with Brownian motion and recall that this is usually defined as a family of random variables. These random variables have special properties. First of all, the first one, or the zeroth of these random variables, is 0, which means simply that the process starts from 0. Then all the increments are independent. This means that if we take values, differences between values in disjoint intervals, then these differences between values are going to be independent random variables. And finally, or almost finally, these increments need to be normally distributed or Gaussianly distributed. It is, as the students probably know, it is quite easy to construct a process with these 3 properties, but the 4th property, which is crucial, makes it very, very difficult to construct such a process. Namely, continuity of paths is a big challenge. But such a process has been constructed by Norbert Wiener at the beginning of the 20th century. Okay, so this is something that students learn in probability or stochastic processes courses, and probably most of them know also, or most of you know, that you may also start a Brownian motion at any point of real line simply by shifting all the random variables by x. What is probably a little bit less known, but for me this is a starting point, is that such a Brownian motion can be described by a single differential operator. This differential operator maps a twice continuously differentiable function into half of its second derivative. Unfortunately, I decided not to explain how this works. In other words, how these 2 objects are connected, because this would lead us into too many technical considerations. So, as I said, I'm just going to assume that you will bear with me and forgive me for such, what should I call it, for leaving all these details aside. But I hope this will be still understandable if you just bear in mind that the operator of second derivative describes Brownian motion, because some features of this process will be then easy to describe. Okay, so Brownian motion, to summarize this slide, Brownian motion is a stochastic process that has values in the real line for the stock. Now, using this basic process, one can construct other stochastic processes. And probably one of the best known variations of Brownian motion, or versions of Brownian motion, is so-called reflected, or in many cases reflecting Brownian motion. The reflecting Brownian motion is constructed from the unrestricted, or this usual Brownian motion in the following way. You just simply reflect all the, can you see my pointer?
Yes.
Okay, so all the parts of the graph that is supposed to describe a Brownian motion, but it is actually, I will speak about it a little bit more later. It is very hard to draw a path of a Brownian motion, but just supposedly that this, on the left-hand side, we see the unrestricted Brownian motion, the reflecting Brownian motion is constructed simply by reflecting everything that is below the t line or timeline above it. So we reflect it upwards and obtain the reflecting Brownian motion. Here is the formula for this. It's a very simple formula. Okay. What is interesting is that, and it's going to be used in the sequel of this, in the remainder of this talk, that if you want to describe this reflecting Brownian motion, you need to use the same operator, same being the operator of half of the second derivative, but you need to restrict this operator to functions with a property that their derivative at 0 is 0. How this is so and why this is so, this would take a considerable time to explain, although this is quite simple. This is doable. So I want you to remember from this slide that from the unrestricted Brownian motion, you can construct the reflecting Brownian motion simply by reflecting its path above the t axis, and that reflected Brownian motion is related to the boundary condition, which is this boundary condition: the first derivative at 0 is 0. Okay, there are other processes that can be constructed from unrestricted Brownian motion. I'm still talking about processes that have values in the right half axis. Namely, you can stop the process after it reaches 0 for the first time. It's quite simple, doesn't need more explanation. Interestingly, if you want to describe this process, you need to look at the second derivative. With the reflected Brownian motion, you had the first derivative equals 0. Now with stopped Brownian motion, you have the second derivative equal to 0, at 0. Okay, I will also use this notion of tau x throughout the talk. So it's worth remembering that tau x is the first time Brownian motion starting at x reaches 0. Okay, so this is of course a random variable. It's different for different omegas, and at such a random time, the process, the stopped Brownian motion is stopped. Okay, there is still another type of Brownian motion called minimal Brownian motion. This process differs from the previous one by the fact that from the time the original process reaches 0, the previous one was kept at 0. This one is left undefined from that point on. In other words, the difference is also that they have different state spaces. As you have noticed on the previous slide, we have right half axis. Here we have an open right half axis. In other words, 0 is no longer a point of a state space. Okay, since we had the second and first derivative, some of you might not be surprised that if you want to describe the minimal Brownian motion, you need to put the boundary condition which says that the value of function f must be 0. Perhaps I should say here, these f's are going to appear throughout and show up throughout my talk. Think of those functions f as test functions, some kind of class of good functions that are going to, as a collection, they are going to describe stochastic process. You may think actually of continuous functions as test functions here, and this is going to be the best choice, at least initially. Okay, So in other words, here we have a kind of summary of what was said up to now. We have from the Brownian motion, the unrestricted Brownian motion, we can construct the minimal, the reflecting, and the stopped Brownian motions. The first one has a boundary condition f of 0 is 0. Second is the first derivative is 0. And for the third, the second derivative is 0. And the particle in the first case, in the minimal Brownian motion, after reaching point 0 is removed from the state space and no longer observed. In the reflecting Brownian motion, it is, well, the path is reflected and the particle just bounces from the boundary that is at 0. And in the third case, a particle, an imaginary particle performing Brownian motion, after touching boundary, just sticks to it, stays there for the rest of its life. Okay, so if we want to stick with processes that are on the right half axis, we may also have combination of these three boundary conditions. Well, this is not what we have here, is not the most general boundary condition, but pretty general. And the P, for P equal 1, this is, and C equals 0. For C equals 0 and P equal 1, we have a stopped Brownian motion. If C is 0 and P is 0, then we have a reflecting Brownian motion. And for P, well, I excluded the case where P, when both second and first derivatives are absent. So in this case, we have processes on the real line with 0, I mean half line with 0 included. Okay, and so you kind of imagine that this boundary condition describes something between those extreme cases. So in other words, the process described by such a boundary condition, this is still the process generated by the second derivative, but with this boundary condition, is going to be a Brownian motion, which after reaching the boundary at 0 will be partly reflected, partly stopped there, and perhaps partly killed and removed from the state space. Okay, so I'm going to, how this removal from the state space takes place, I will explain in the next two examples, namely in the case of P equal 1, C is then non-zero. This is called elementary exit. And the second example where P is 0 and C is non-zero, then this is called elastic Brownian motion. Okay, this elastic.
Excuse me, I have a question. So you do you have in mind that with some probability is removed, with some probability reflected, and with some probability captured?
Well, the use of the word probability is here.
Or we have inner measure, yes.
Yeah, but this is a bit more complicated than so that's why I have tried to use the word combination, because this is not strictly probability. You cannot say that with some probability this happens, and with that probability that happens. It's slightly more complicated than that. So I wouldn't use the word probability, but otherwise this is a combination. So you have partly this, partly that. Okay, is it agreeable?
No.
Okay, so maybe this will become more clear a bit later. What I'm trying to say is that you cannot use the word probability of capture, of reflection, of removal, just by looking at this boundary condition, because these P's and C's, they do not stand for probabilities per se. Okay, this is slightly more complicated than that.
No. I didn't have in mind the constant, but I was thinking that we have a differential operator that I think it's the second derivative. Yes. And you have boundary conditions and you have certain diffusion behind.
Yes.
So how should we understand this diffusion in terms of this minimal reflecting and stopped?
This is what I'm going to explain on the next slides.
Okay.
But this is a very good question. Many people think that these coefficients here, they describe probabilities.
No, I didn't have that in mind. No. Okay.
Okay. So, so let me talk about elementary exit Brownian motion first. This is the boundary condition, the particular case of a boundary condition described above. In other words, we take P equal 1, so that the second factor, second term disappears, and we obtain a boundary condition like that. And this is called, as I said, elementary exit. So this elementary exit Brownian motion looks as follows. After reaching the boundary, the process stays at the boundary for an exponential time. This exponential time has parameter c, precisely the c from the boundary condition. And this time is independent from the entire Brownian motion. So it doesn't matter, I mean, the Brownian motion doesn't influence the t in any way. And after this exponential time is over, the process is undefined. Okay, so here on the picture we have the unrestricted Brownian motion. From the moment it touches the boundary for the first time, it stays there, the elementary exit stays there at the boundary, but stays there for an exponential time only. The reason why it needs to stay for an exponential time is that the Markovian nature of the process needs to be kept, needs to be retained. Okay, so this is the simplest situation. Now, there is also, and I want you to note on this slide that C is the rate with which probability mass escapes from the at the boundary. Okay, so the larger is the C, the faster the process disappears after touching the boundary. Okay, so it's going to be quite similar for so-called elastic Brownian motion. And this is going to be quite similar, but also much more complicated in a sense. So to explain this, I would like to ask you the question of how many zeros does reflected Brownian motion have. Okay, if you look at pictures that come to our mind when we want to graph a continuous functions, it may seem like on this one, it may seem that zeros of Brownian motion form a very simple set, you know, disjoint, maybe even finite number of points where Brownian motion intersects the T line. But this is completely off. This is completely misleading. It's because our imagination comes short of imagining of drawing in our mind a picture of a Brownian motion. These paths of Brownian motion, they are much more complex. And so to explain a little bit more why this picture is misleading, we need to recall the following fact. If you take the maximum of a Brownian motion, and from this Brownian motion, from this maximum, you subtract the original Brownian motion, you will also obtain a reflecting Brownian motion. Let's look at the pictures because they give us more intuition. Okay, so we start with a standard Brownian motion or unrestricted Brownian motion, starting at 0. Okay, and then we look at the maximum of this path in larger and larger intervals. So this looks like this. Finally, we subtract from this maximum, we subtract the original path. And what we obtain, of course, is something that is always larger than 0, starts at 0, and it turns out that this is again a reflected Brownian motion. It is indistinguishable from the Brownian motion constructed on the first or the second slide by taking a absolute value. These paths also form, as I said, a reflected Brownian motion. Now, the difference between the first one, the first construction, and the second construction is that here it seems like for long intervals, we'll have zeros here in the difference. Because those, well, on this picture, you can see some short intervals at least. If you zoom in a little bit, and you will see some short intervals. They come from the fact that 0 in the difference is precisely when the maximum is equal to the function. So the maximum equal to the function means these are the intervals when Brownian motion increases. Okay, so when Brownian motion increases, the difference should be 0, the difference between standard and maximum, standard Brownian motion and its maximum. So from this picture, it would seem like zeros of Brownian motion have long intervals. Okay, so let me tell you that none of these pictures is true. In fact, sets of zeros for Brownian motion are Cantor-like. So these are very complicated sets, but due to the work of Paul Levy in the beginning of the 20th century, very particular, very important stochastic processes called local times were constructed. On this slide, this local time is called sigma, although it's usually denoted tau. I just wanted to distinguish it from tau being the first time a Brownian motion reaches 0. So this local time measures the time spent by the process at the boundary. Okay, so if I have not lost you yet, let me hasten to add that how elastic Brownian motion is constructed from the reflecting Brownian motion. Well, simply the local time measures how many times or how long a time the process has spent at the boundary where x is 0. And when this time, called sigma, is larger than an independent random variable with a parameter c again, as was in the case of elementary exit Brownian motion, the elastic Brownian motion is again undefined. So in other words, the path is cut at a random point. Okay, and this but this random point depends on how many times well, this is not strictly speaking true, but just figuratively speaking, how many times did the Brownian motion touch the boundary? The more it touches the boundary, the larger is the probability that the path will be cut short. Okay, so does it answer the question that you had? Because that's the more precise description.
Well, in a sense, so I imagine that this elastic Brownian motion is just reflected up to some random time and then stopped.
Yes, yes, but as you see, this is not because some people, when they look at this boundary condition, even very well-known specialists, they would say that at each time that Brownian path touches zero, there is a probability of this being reflected or stopped or killed. But here, it's a different story, as you see. Okay, this is a very subtle point. The time or the measure of the time the process stands at the boundary is taken into account, and this measure influences how long the process will continue. Okay, so this is very precise description. But I wanted you to I wanted all the people in the audience.
So if you take combination of three things, I mean, reflected, stopped, and undefined, then you will have two random times, and up to one time, up to first random time. No, it's not.
Okay, this is, well, in other words, each time. Okay, maybe let's look at this boundary condition. Okay, so with each combination of P's and C's, or for each P, there is a different local time. For P equal 1, this local time is simply the usual time. For P equals 0, this is the local time introduced by Paul Levy. Now for P between 0 and 1, this is going to be well, a different local time, which is because the particle will have for P closer to 1, the particle will have a tendency to stick to the boundary for a longer time.
Mm-hmm.
Okay.
And so, then may continue as reflected or not?
Well, depends on whether C is positive or not.
Ah, okay.
If C is positive, then it may continue, but after a certain time, it will be removed from the state space.
Okay. Mm-hmm.
Okay. So in other words, here is the summary of what I have said before. I mean, up till now, in this boundary condition, the larger is the P, the more sticky is the boundary. So in other words, a particle may, once it touches the boundary for the first time, it is kind of glued to it, but may, as you have asked, may come back to being a reflected Brownian motion.
Yes. Okay.
Okay.
Mm-hmm.
But there is some degree of stickiness at the boundary. Whereas for P equals 0, there is no stickiness.
Mm-hmm.
So the boundary is rigid. Okay. So the smaller is the P, the more rigid is the boundary. Mm-hmm. The larger is the P, the boundary is more sticky. Okay. Now, but independent of these two parameters, we also have a parameter C, which describes how many particles or how often particles are being killed at the boundary. Okay, the C, you might remember that C was the exponential was the parameter of an exponential random variable. Okay. So the larger is the C, then expected time spent at the boundary, quote, is shorter. Okay, so this is, the smaller it is, the longer is the time spent at the boundary. Okay, but as the title says, there is something new on this slide also, namely, not yet the most general boundary condition, but very, very, very close to the most general boundary condition is as follows. We add another term to the right-hand side, and in this term we have simply an integral with respect to some probability measure over the entire open half axis, and this is multiplied by a coefficient d. This d must be no larger than c. This is positive, but no larger than c from the left-hand side. So what does this describe? Namely, it describes the following situation. The left-hand side says that after some random time, the process we are describing may be left undefined. Now, d divided by c, that's why we needed d smaller than c. D divided by c is the probability that the process starts anew. So after being killed and removed from the state space, it comes to life again somewhere in the state space. And the measure p describes its starting point, new starting point. In other words, after being killed, the process starts anew at a random point, which is described by the measure p. Okay, so this is almost the almost general boundary condition for a process with boundary at 0. Okay, so 0 is a special point for such processes. Okay. May I continue?
May I also ask a question, please?
Sure.
So I'm still wondering about the function f, and is there some relation to Ito's formula, or could you say only in a very simple words where that f originally comes from?
Well, the f's are, just think of f's as continuous functions. You know, I come from semi-group theory, so for me this is to describe a process I need an operator in the space of continuous functions on the right half axis. Mm-hmm. So you can think of f's as such functions.
A completely different approach then. So Ito is not involved.
Ito is not involved.
Okay, thank you. Yeah, just to get to understand slightly bit better what this f actually does. Yeah, thank you. Thank you.
Again, f is just a test function. I'm sorry for this, but no, thinking in terms of Ito formula would be misleading.
Okay. Yeah. Thank you.
Okay. So I'm almost done with all those various kinds of Brownian motions, and what I would like to say now, is modeling of semi-permeable and permeable membranes. So that's my second part of the talk. That all that I have said till now is pretty standard. This has been known since I don't know, 1960s of the previous century. A great work by William Feller in particular, and the Russian mathematician Wenzel. these are those famous boundary conditions, Feller-Wentzer boundary conditions that I have just described. Okay, now we turn to semi-permeable membranes. So this is a situation where you need to change test functions. These test functions that I'm going to use are going to be continuous on the entire on the entire line, except at 0, where they have left limits and right limits. This is because 0 describes the membrane. So you kind of distinguish between what is on to the left of a membrane from what is to the right of a membrane. For simplicity, I have a diffusion process on the left, just Brownian motion, and I also have Brownian motion on the right. But what is missing, if you just say Brownian motion and there is a membrane, you need to what is missing in the description is what happens to the particles that touch the membrane. So this is described by so-called transmission conditions, just to distinguish them from boundary conditions, but they play a very similar role. So let's look at the left boundary transmission condition and forget about the right one for a moment. And just for a moment, just think that this factor f of 0 minus is not there. Okay, so this is not in this boundary condition. What would this describe? This would be simply the boundary condition for elastic Brownian motion, yes? So in other words, we have this process that takes on the right-hand side, which is being reflected from the boundary many, many, many times. And after a random time related to this mu, the process is left undefined. Okay. Now, so we have the case already described. Now, what happens if we add this term that I have just dismissed just a moment ago? Well, this could be seen as an integral. This f of 0 minus can be seen as an integral over with respect to Dirac measure that is situated at 0 with a minus. So at the very close to the membrane, but on the left, just outside the membrane, but to the left. So, and if you look at the previous slide, so as I said, this is the p is now 0. So we have f prime of 0 plus cf of 0, and d. So c is mu, and d is also mu, and this p is the Dirac measure. In other words, this boundary transmission condition describes the following process. It is being reflected from the right, when started at the right-hand side, it is being reflected from the boundary many, many, many times. And after a local time is long enough, that a particle, instead of being killed and removed from the state space, it filters to the other side of the membrane and starts from 0, but to the immediate left of the membrane. The second boundary transmission condition has precisely the same form. So it describes the situation in which a particle starting on the left is being reflected from the boundary many, many, many times. And after the time spent at the boundary is long enough, the particle filters to the right-hand side and starts from 0 also, but the immediate right of the membrane. And as you might remember from the previous slide, the mu and nu, they play the role of a coefficient C. In other words, the larger is the mu, the larger is the nu, the easier it is for particles to filter through the membrane. Okay, so this process is called snapping out Brownian motion. And such, for some reason, some time ago, I was interested in the situation where these permeability coefficients are very large. In other words, I want to multiply both mu and nu. They are different now. I multiply them by n, and I want to take the limit as n goes to infinity. I wanted to have mu different from nu because why should the membrane be the same from both sides? In particular, in biology, you have, here is the only point that I will speak about biology. In biology, in living cells, in living organisms, there are myriads of semi-permeable membranes which act differently when approached from one side than when approached from the other side. You know, even all those jackets that you have, you know, you need to breathe. They need to breathe. But on the other hand, you don't want them to absorb water. So you know, this is a typical situation where mu and nu are different. Okay, so coming back to my subject. Some time ago, I wanted to study the limit when permeability coefficients increase to infinity. So, you know, intuitively, you might think that in the limit, and this is what I thought, in the limit, we will obtain a completely permeable membrane, yes? Because if permeability coefficients are infinite, then it means, you know, immediately after touching the boundary, a particle goes to the other side. Well, but if you look at these boundary conditions, they are quite interesting. If you suppose you divide the first boundary, transmission condition by n mu, and you divide the second boundary condition by n nu, then the right-hand sides are completely the same. So in the limit, when n goes to infinity, you will also have the left-hand side the same. So this leads to the following boundary conditions that you obtain in the limit. Well, first of all, I should have said that if n goes to infinity and you divide the first and the second transmission conditions by n, then the right-hand sides are going to be 0, which means that the values of 0 from the left and from the right need to be the same. So that's the second transmission condition here. Now this is the first boundary transmission condition. That's very funny. Okay, but before I will continue, I would like to say a little bit about technicalities. This convergence that I have just spoken about, this was hand waving, but you can make it this is a strict mathematical result. This is convergence of corresponding semigroups, and you can do that in the spaces that you want to, namely in the space of continuous functions or in the space of integrable functions. This implies weak convergence of processes. There are also some more delicate phenomena like convergence of related cosine families. I do not want to touch this, but I wanted to make sure that you know that this is not just hand waving. This is a very strict mathematical result. Convergence of snapping out Brownian motions to something that is really strange. Namely, on one hand, we would like to think that in the limit, the membrane is completely permeable. But on the other hand, we definitely see that there is some kind of asymmetry in the way particles filter from one side to the other. Yes, this boundary, this transmission condition tells you that there is something strange going on here, like in Orwell's Animal Farm. You know, there is apparently both sides are the same, they are equal, but one is more equal than other. Okay, so I'm coming to the main topic.
So excuse me, so is it more likely to go from right to the left or from left to the right or something like that? Something like that, yes. Mm-hmm. And the question is, how do you describe this? How do you make it more precise? Okay. Even though permeability is infinite from both sides, in a sense, it is easier to go from one side to the other than the opposite, as precisely as you have said. Okay, so we do have a very precise description of approximating processes, but it's rather complicated, as you have noticed. Do we have a description of the limit process? Well, it turns out that this process is precisely something that has been known for over 50 years and is quite simple. So I'm just repeating the boundary conditions. And it turns out that the entire process can be described by just a single parameter. Well, this comes from the fact that you may divide the second boundary condition by mu plus nu, and you will obtain alpha, which is nu divided by nu plus mu, and 1 minus this on the other side. So this one key parameter describes the entire process. So how does this Skew Brownian motion look like? The construction is as follows. This construction is due by Ito, McKean, and then later on John Walsh has worked on this process quite a bit, and his work has led to a number of generalizations. So construction is as follows. You start with the unrestricted Brownian motion as on the left-hand side. Then you construct the reflecting Brownian motion just simply by taking everything that is below the T line above it. And now you look at so-called excursions. The first excursion is seen here between V0 and Z0 is the first excursion of a process. Then between Z0 and Z0 is the second excursion, and so on and so forth. With each excursion, you either leave it above or with probability alpha reflected downwards. So in this picture, several of the first excursions were not reflected. And this one, this long one excursion has been reflected. The second one, the next one was not, and so on and so forth. So in other words, for each excursion with probability alpha, you leave it above, or with probability 1 minus alpha, you reflect it downwards. That's very simple. That's precisely construction of Skew Brownian motion. No local times. And there is, here you can be more precise about this feature that we have noticed, that it is easier to go from one side to the other than in the opposite direction. Precisely this alpha is the factor that tells you how much more probable it is to, how much easier it is to go from the left to the right than it is from the right to the left. Okay, so this is this funny object.
maybe I should say that there is a number of generalizations. For example, so-called Walsh's spider. You may have a spider going on arrays like this, and when it comes to the center of a spider web, with quote probability, it chooses one of those other arrays, arrows, to continue its motion. And there is a boundary condition for there is a number of generalization of this process. There are these nice books of Portenko and also an article of Lejai. Okay, but the main point is that this skew Brownian motion describes a situation in which there is a trace of boundary of semi-permeable membrane at a certain point. Okay, and here is the second. How much time do I still have? Oops, almost no.
No, 5 minutes, okay.
I'm sorry, how many?
5 minutes, okay.
Okay, so just very briefly, I will speak about kinetic model with interface. Namely, okay, imagine two lines. On the upper line, a process that we want to describe moves to the right with constant velocity. On the lower line, it goes to the left with the same constant velocity. There is also an interface at zero, somewhere in the middle of these lines. So if a process going from on the upper line touches the interface, with probability P, it goes still farther, but with probability 1 minus P, it is being reflected and goes to the left on the lower on the lower line. Analogously, when a process going on the lower line touches the interface, with probability Q continues its motion with the same speed, or it may be reflected and go to the right on the upper line. The process, these lines also are related, but I mean, a particle moving to the right on the upper line may also jump from the upper line to the lower line at the epochs of a Poisson process. In other words, every exponential time it may jump, and when it is on the lower line, it may go back to the upper line, also at the epochs of the same Poisson process. Okay, next we do so-called the diffusion approximation, namely intensity of jumps is increased. Epsilon is a very small number, so jumps are very, very frequent. Now, the velocity of a particle is also larger, but of one scale smaller than intensity of jumps. What happens when you let the epsilon go to infinity is in the case without interface, this is a very classical result. Namely, jumps are so frequent that you cannot distinguish between points on the upper and lower lines, I mean, the corresponding points. So in the limit, you will obtain just a process on a single line, which, on the other hand, may go either to the left or to the right. This process turns out to be a Brownian motion. Now, if you add the interface, the result is pretty much the same, except that in the limit you will obtain the skew Brownian motion, not the unrestricted Brownian motion. In other words, the interface, I'm sorry, the title is in Polish, so I did not notice that. In the interface modifies the limit Brownian motion by making it, by turning it into a skew Brownian motion. Okay, thank you. Thank you very much. Sorry for extending my
Thank you. Thank you. Questions?
Okay, I may ask questions. So this skew Brownian motion, or this Brownian motion constructed at the beginning with P and C, they are related to some applications?
Yes, yes. In many situations, in modeling neurotransmitters, in modeling activity of kinases, there is just myriads of situations where you model diffusion processes in biology by looking at very particular boundary conditions. Yes, and not only in biology, of course, also in physics.
Okay.
And they lead, of course, to many interesting singular perturbations. And not, I mean, this is there is a number of papers showing that if you do not impose proper boundary conditions, your results, your conclusions may be misleading. And so the proper modeling of biological phenomena involves boundary conditions very much.
Okay, and then this can be done in 2 dimensions, 3 dimensions, yes?
Yes, but of course, this is much more complex.
More complicated, yes,
yes,
of course.
Yes.
Oh.
So, for example, working in the space of continuous functions in dimensions 2 and 3 and larger, this is very difficult. So, like all the analysis presented here was in the space of continuous functions, but in higher dimensions, you need to go to LP spaces or things like that, and then it is more difficult to interpret this in stochastic terms.
But for applications, is it enough to consider one-dimensional case, or you need to consider more dimensional cases?
In some cases, like for example, I have worked on a model by Tomasz Lipniacki, who is one of the leading experts in signaling pathways. And in some cases, you may assume that, for example, a cell is symmetric in a sense that processes. If you imagine a cell as a ball, two-dimensional ball, or you may think that processes going that take place in the cell that are say distant, equidistant from the center of the cell are pretty much the same. So sometimes you may reduce two-dimensional models or three-dimensional models to one-dimensional models. Yes.
Okay, thank you.
I would like to ask a question related to the previous question. So in this higher dimensional setting, we no longer deal with continuous function. Instead, we have to somehow consider functions lying in some negative Sobolev spaces, for example. It could happen. Mm-hmm. And my question is, for this kind of generalized function, the value at a particular point does not make sense, but still, is it correct to think that somehow we can define what does it mean to the set of the zeros of this function to be of the positive measure, even if we don't have a precise meaning of a value at some point? But you see what I mean?
Oh, but you are apparently mixing up two things. One are test functions, and the other thing is the paths of a Brownian motion. The path of a Brownian motion is always going to be a continuous function. Now, test functions is a different story. Did I understand your question correctly?
So I meant something like, for example, in the 2-dimension, the analog of a Brownian motion is this Gaussian free field, and this is no longer a continuous function. This is something like a generalized function. It belongs to the negative Sobolev space with.
No, but paths of a Brownian motion are still continued. I mean, continuous. So if you want to think about zeros of a Brownian motion, that's precisely the same.
I rather would like to think of something like zeros of a Gaussian free field in higher dimensional setting. So this is
okay.
somehow related to this.
You know, this is a different story because even in 2 dimensions, the probability of hitting, or is it in 2 or already in the 3 dimensions? The probability of hitting 0 is 0 if you start from somewhere else. So this is a different story.
Okay, and maybe
for a Brownian motion.
Okay, and maybe just one more question, slightly related to that. So at some moment you mentioned that this set of zeros is a counter-like set. So it is like a counter set in the topological sense, yes, but still it is of some positive measure, yes? Or
no, well, for the Levy Brownian motion, I mean for the reflected Brownian motion, it has measure 0.
Okay, it has measure 0. Okay,
it has measure, but for the sticky Brownian motion, in other words, when P is not what was it? P is not 1 or P is not whatever. For the sticky Brownian motion, it may have when P is larger than 0, the set of zeros may have the measure larger than 0.
Okay, but will it be still like a counter set, or
well,
it would contain some interval?
I'm not sure about it. This is where my knowledge ends. But to my understanding, it might contain open intervals, but I cannot be completely certain about this.
Okay. Okay, thank you.
Even if there are such small intervals, they are very, 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 very small.
Any other questions, either here on site or online?
I would have a question online. Is this already possible, or are you still asking in the audience?
I'm sorry?
I would like to ask a question, but it's online. So are you still in the audience asking? The round is in the audience?
You go ahead, ask the question.
Okay. So my question is related a little bit related to the stochasticity. And is a Skew Brownian motion a continuous martingale with respect to the filtration originating from the original Brownian motion?
I didn't quite understand your question. So maybe this is just a technical difficulty, but
okay. So
all I have. Did you say something about martingale?
Yes. Yes.
So
if you have standard Brownian motion, very basic case, the unrestricted case, it's well known that this standard Brownian motion is a martingale with respect to its own filtration. That's known. That's the standard. And my question is whether Skew Brownian motion also does satisfy this property.
That's a very nice question, but I do not know the answer.
Okay, because if it were, you could use a theorem that every continuous martingale can be represented as time-changed Brownian motion.
But so are you trying to say that the Skew Brownian motion might be a time change of a of the unrestricted Brownian motion? I think I think this is not the case. But of course, this is just my speculation, because a time change changes the generator. Could be. Well, yeah, that's a nice. No, I'm backing off. Maybe it could be the case. I'm not sure. Could be. It could be the case because this is okay. There is the but this would be a very singular perturbation of the generator. If you are familiar with this description in terms of what is it called, speed measure and whatever, just like a Feller Laplacian, then there is a description in these terms also. You have like every stochastic or almost every stochastic process, every nice stochastic process can be described by the generalized Laplacian of William Feller. And then you have two characteristics there, and probably this is the perturbation that you would obtain. This could involve random time change. Yes.
Okay, thank you. I'm not an expert in this field, so regarding how the generators work, but I'm really interested in the stochastics, which is behind these processes, and the time change is often a very nice tool to use.
Yeah, but this time change that you are talking about would probably be quite singular at zero. So I'm trying to figure out how this would look like, but I believe I have seen something very similar somewhere.
It's a quadratic variation time. So if you have a continuous martingale, let's call it M, and then M is B capital T. T is a random stopping time.
Yes,
which is induced by the quadratic variation of Brownian motion.
Yes.
What
I'm trying to say is that usually the time change results, if you want to look at the generator, then a time change results in multiplying the generator by a function. So but here, this skew Brownian motion doesn't change the generator. It changes only its domain. So in other words, this, instead of multiplication of generator, you have a change of its boundary conditions. So so it would need to be very tricky, very singular time change.
Thank you. Thank you very much.
Okay. Any other questions? Well, if not, let us thank the speaker again.
Thank you very much for inviting me.
Thank you, Adam, for coming here.